Welcome to the podcast, everyone. I'm Hari.
And I'm Kimi. Today, we are literally bridging the gap between history, engineering, and culture by discussing a structure we interact with all the time, the bridge.
It is a fantastic topic. A bridge is fundamentally designed to span an obstacle, like a river or a deep valley, allowing vehicles, pedestrians, or even trains to pass across. But the evolution of how we do that is just remarkable.
Absolutely. It all started with incredibly simple forms. Around 4000 BC, people in Switzerland were using pilings to support stilt houses, allegedly over water, though archaeological consensus shows they were actually constructed on marshy land. The earliest actual bridges were just simple wooden boardwalks or logs crossing wetlands.
But it didn't take long for ancient civilizations to step up their game. By the 13th century BC, the Mycenaean Greek culture was building corbel arch bridges. The Archidico Bridge is one of them, and amazingly, it is still in existence today.
That is mind-blowing, and we can't talk about ancient engineering without mentioning the Romans. They built durable aqueducts and bridges using a semicircular arch style. They even used a special waterproof cement mixed with volcanic ash.
Right. That waterproof volcanic cement was a total game changer. It allowed them to build structures like the enormous timber and stone Trajan's Bridge around 105 AD, which crossed the Danube River and was over 900 meters long.
And let's not overlook ancient Asia. China has a brilliant history of bridge construction. The Anji Bridge, built during the Sui dynasty around 600 AD, is historically significant because it's the world's oldest open spandrel stone segmental arch bridge.
Meanwhile, in the Andes Mountains, the Inca civilization was making suspension bridges out of ropes and vines long before Europeans ever arrived. It really highlights how different cultures solved the same geographical problems with their local resources.
Exactly. Fast forward to the Renaissance in Europe and we see a huge shift. Figures like Galileo Galilei and Andrea Palladio began applying a rigorous analytic approach to architecture. This scientific emphasis led to elegant stone segmental arches like the Rialto Bridge in Venice.
But the real structural revolution came with the Industrial Revolution. Before that, bridges mostly carried pedestrians, horses, and carriages. Suddenly, the age of railways began in the 1820s, and everything changed. Trains are incredibly heavy. A single locomotive can weigh up to 197 tons. Railway bridges had unique requirements. They had to minimize bending under load and tolerate the heavy impact of wheels striking the tracks. Which is why early railway engineers in industrialized nations stuck mostly to heavy masonry and stone arch designs. They completely avoided curved bridges, suspension bridges, or cable-stayed designs for trains, instead favoring straight beam or truss bridges.
In North America, however, lumber was so abundant and inexpensive that they favored timber for their railway bridges, using truss designs for long spans and trestles for deep ravines.
Eventually, the mass production of steel provided a stronger, lighter material. Steel replaced iron, allowing for complex truss and cantilever forms. And it revolutionized suspension bridges, allowing bundled steel wires to replace the older iron eye-bars.
That innovation is what ultimately allowed spans to reach epic proportions. In 2022, a bridge span exceeded 2 kilometers for the very first time with the 1915 Chinookele Bridge.
That is over 1.2 miles for a single span, just staggering. Let's talk a bit about the basic structures used today. Most people know the arch, the beam, and the suspension bridge, but there are also truss, cantilever, and cable-stayed bridges.
People often confuse suspension and cable-stayed bridges. In a suspension bridge, the deck is hung from massive curved cables draped between two tall towers. But in a cable-stayed bridge, the supporting cables connect directly from the towers to the deck, usually in a fan or harp pattern.
And cable-stayed bridges are often chosen because they use less cable for a given span size and don't require the massive ground anchorages that suspension bridges do.
There is also a fascinating hybrid called an extradosed bridge. It combines features of a box girder bridge and a cable-stayed bridge. The towers are relatively low, and the cables actually compress the deck horizontally.
I love the odd ones out, like movable bridges. You've got bascule bridges with counterweights, swing bridges that pivot horizontally, and lift bridges. The Gateshead Millennium Bridge over the River Tyne is a really rare example of a tilt bridge.
And we can't forget double-deck bridges, which carry two decks on top of each other to maximize traffic flow in tight spaces. The George Washington Bridge in New York has 14 motor vehicle lanes, making it the world's busiest bridge. It carries over 100 million vehicles annually.
Beyond transportation, some bridges serve really surprising purposes. In the modern era, some highway rest areas literally span the highway as bridge restaurants. The Novi Most Bridge in Bratislava even features a restaurant set right atop its single tower. There are also wildlife crossings designed to reduce habitat fragmentation, and military bridges that are critical in wartime. Armored vehicle-launched bridges can deploy a temporary span in just minutes. And the classic Bailey Bridge from World War II is still used in peacetime today for temporary repairs.
Speaking of wartime, bridges are major targets because they are immobile, easy to spot, and taking them out disrupts the enemy's transportation network. Germany dive-bombed them in World War II, and more recently, drone attacks damaged the Crimean Bridge in 2023.
That brings up the incredible stresses that bridges have to endure, whether from human conflict or natural forces. The structural load of a bridge is divided into the dead load, which is its own weight, the live load from traffic, and the environmental load.
Right, the environmental load includes winds, earthquakes, mudslides, and floods. Designers actually use a return period to calculate maximum severity. For a critical lifeline bridge, they might design it to withstand the strongest storm expected to happen once every 2,500 years.
And unfortunately, when engineers miscalculate those forces, the consequences are tragic. In 1940, the Tacoma Narrows Bridge collapsed in winds of just 68 kilometers per hour because the designer failed to account for wind-induced flutter and resonant vibrations.
It's a sobering reminder. Failures still happen. In 1996, the Koror Babeldab Bridge in Palau collapsed just 3 months after a repair operation. And in the U.S. today, about half of all bridge failures are due to flood damage or scouring, which is when water currents wash away the sand and rock supporting the footings.
Scouring is a huge problem. That's why underwater foundations have to be rigorously inspected, usually every 60 months. And construction underwater is inherently dangerous. In the 19th century, workers used caissons, watertight structures sunk to the riverbed. But they didn't understand decompression sickness yet.
Yes, that was a grim chapter in civil engineering. When building the Eads Bridge, 13 workers died because they didn't properly decompress when exiting the caissons. Today, safety protocols are much stricter, and bridge engineering is a highly regulated profession.
To prevent failures now, managers use non-destructive testing techniques. Visual inspection isn't enough, so they use ground-penetrating radar, ultrasonic pulse velocity tests, and even X-rays to assess the condition of the concrete. And routine maintenance is a continuous battle against the elements. A bridge's steel components typically need painting every 12 to 15 years to prevent rust, and bearings need lubricating every 4 years. Concrete has to be protected from freezing, thawing, and sea spray.
Which costs a lot of money. Funding comes from fuel taxes, tolls, and increasingly public-private partnership agreements. But toll booths are actually quite inefficient because they slow down traffic.
Beyond the engineering and economics, we have to touch on the societal impact. A new bridge can drastically reduce transport times, boost a region's GDP, and help bridge the gap between prosperous central regions and less developed rural areas.
Though they do have downsides, they can proportionally increase environmental pollution. Furthermore, the production of massive amounts of concrete for modern bridges significantly contributes to global greenhouse gas emissions.
There is also a very serious issue regarding mental health. Tall bridges in urban areas can attract individuals experiencing a suicidal crisis. It's a sad reality, but installing suicide prevention barriers on high-risk bridges has been proven to dramatically decrease the suicide rate on those structures.
It is a heavy topic, but an important one for city planners to consider. On a brighter note regarding society, bridges hold a deep symbolic meaning in our culture. They're frequent metaphors in art and literature for connection and transition.
Think of Norse mythology, where the Rainbow Bridge Bifrost connects the Earth to Asgard, or how many medieval bridges in Europe are named Devil's Bridge, complete with folkloric legends.
And I love the story of the Euro banknotes. In 1996, the European Commission chose illustrations of bridges designed by Robert Kalina for the currency. They were specifically chosen because they symbolize the links between states in the Union and paths to the future.
That's a beautiful metaphor. The art historian Dan Cruikshank pointed out that a great bridge has an emotional impact and a heroic beauty that moves people. Look at signature bridges like the Golden Gate Bridge or the Brooklyn Bridge. They completely define the identity of their host cities.
They truly are monuments to human ambition and imagination. From a log over a creek to a 2-kilometer suspension span, bridges show just how far we're willing to go to connect with one another.
A perfect thought to wrap up today's deep dive. I hope you all think a little bit differently the next time you drive, walk, or take a train across one of these engineering marvels. Thank you so much for joining us on this journey. Take care, stay curious, and we will see you on the next episode with another fascinating topic. Have a wonderful day.
This episode is based on the Wikipedia article Bridge, which is available under the Creative Commons Attribution Share-alike license. This podcast was crafted using artificial intelligence.